Hello and welcome to podcast number 38. Still doing alkene chemistry. So for this particular one, we're going to do bromination and more generically something called halogenation, where we'll add either Br2 across a double bond or Cl2 across a double bond, and then epoxidation, where we'll oxidatively insert an oxygen to a pi bond to end up with a three-membered ring, two carbons and an O, highly ring strained, highly unstable. So it's a great intermediate for forming diols amongst other things. But we'll go into that details as we go. But with no further ado, I don't know if that was the right sentence, but it sounded good. We'll go ahead and start with bromination. So as always, I'm starting with this compound. So the 5-carbon chain with the methyl, so 2-methyl 2-pentene. And again, doing it so that I have asymmetric. So I have 2 carbons on this carbon and only 1 here. So we have a choice of regioselectivity. And as the product shows, we'll have a choice of stereoselectivity as well, because we get a stereo center in that spot. So I hope that the very first thing you do is when you look at this reaction, you go ahead and make a decision about exactly what has added onto that double bond. So there's always one thing adding to the left carbon, one adding to the right, which figure out what that thing is. In this case, it's a pair of bromine atoms. So stereoselectivity, this is up, this is down, so we refer to that as anti. And then regioselectivity doesn't matter because they're both getting the same atom, bromine. We'll talk about some regioselectivity as we get a little more detailed on this, but just at this simple stage, they each get bromine, bromine on left, bromine on right. But the one thing you should note, they are not syn. They're anti to one another, which means they do not add at the same time. When you add at the same time, you add syn. When you add one at a time, you end up adding anti. So the first one that goes on, let's say it adds to the top side is now crowded, so the second one will come in from the back side. Or if the first one adds from the back, then the second one has to add from the top. So the addition of one creates steric hindrance that influences the addition of the second one. So we'll go into the mechanisms of this, but for now, I just want to, again, pay attention. One bromine goes on first to form what's going to be called a bromonium bridge, where it inserts into the pi bond. So kind of like the epoxide I was talking about, it forms a 3-membered ring, but it's not a perfectly balanced 3-membered ring. So very much like oxymercuration, where the mercury added to one and coordinated to the other, it's kind of the same thing, where it'll add to the less hindered and coordinate to the more hindered. So one goes on first, and then the second one comes on anti to that first one. So one goes on, second one comes on opposite side, hence the anti addition. Okay, so regioselectivity, again, we look at this, there's a bromine on each one, so none in this case. And then stereoselectivity, anti-alignment, anti-orientation. So if one adds on bottom, the other one adds on top. Perfect. For the mechanism, so that bromonium bridge is the key player in this. So the double bond, as is the case for all our reactions, is the nucleophile. It's going to send electron density to bromine. That represents one pair of electrons too many, so this will kick out as such. So I'm going to go ahead and let the arrows do their thing and get rid of the ones I drew. And so now one of the bromines is on. And so at first, the bromine is here, just like the mercury with OAC, the plus for that one, it added to the less hindered. First one in adds to the less hindered, leaves a carbocation on the tertiary. But this lone pair is close enough that it can actually stabilize it. So this lone pair will come in and attack the carbonyl, or not the carbonyl, excuse me, the carbocation, and it forms what's known as a bromonium bridge. But notice, just like the mercury one, I have the solid line and the dashed line. So it forms a very strong bond here, full covalent, but this one, kind of a partial covalent. So it's still there, it's still a viable covalent bond, but it's not as strong as the first one, simply because of sterics. So it's going to favor the less crowded side. So it's not a perfect triangle as you see, it's kind of off-centered. The plus charge that's here is going to be shared across the bromine and the carbon. So we call it bromonium ion, or bromonium bridge, because it's positively charged bromine. So bromonium means partly positive. So hopefully this seems reasonable. This is where that other Br then is going to come in from the backside. It comes into the tertiary because this is the more available carbon, because this is only a partial bond right here. This has a bigger plus charge than this other side. Negative seeks out positive, comes in and attacks, breaks that bond from the backside, so you end up with anti-orientation. So this bromine came on top. This one is going to be knocked to on bottom. Note that this bromine could have also come in on top in this other step, and we would have ended up with anti as well, but with this bromine down and this bromine up. So we would have gotten the same thing, but in enantiomers. So the same anti arrangement, but it would have been S instead of R, or R instead of S. So let's just calculate real quick. 1, 2, 3, clockwise, but H in front. So this is S. So we would have got R instead of S at that center. And this, again, is not a chiral center because two methyls are identical. Okay, so want to do a few twists on this. So again, we know it's anti, and we know it goes through that bromonium ion bridge. So the bromonium ion is that bromine inserting into the pi bond. So what happens instead of doing it in CCl4, where bromine is both the electrophile, goes on first, and the nucleophile, which comes in and displaces it? Note that if we used water, a better nucleophile than Br, then, and I should be careful saying better, the real major reason, if water's in high concentration, it's a solvent, then the probability of water attacking the carbocation that forms there is far higher than bromide, the Br minus attacking it. So instead of opening up by attack of Br, it opens up with the OH. And then we can also make note that if we were to do it with Cl2, and I've changed solvent, no, for no other reason, just happens to work cleaner with that one. But notice that CCl4 HCCl3 really doesn't make that much difference that I'm using that solvent-wise. But what is important here is it's the same process, except it's a chloronium instead of bromonium bridge. So you form the Cl, again, it's an asymmetric bridge. Second one comes into the backside. So like I mentioned, I went ahead and did this anti, up, left, and down, right, up, left, down, right, up, left, down, right. But each one of those, you should make note, forms the enantiomer as well. And one of the points that we're going to make on these is that because it starts optically inactive, it must finish optically inactive, which means you must get a racemic mixture, 50-50, 50-50, 50-50. Okay, so this opens up a few doors for us. The two bromines, the two chlorines, so bromination and chlorination, but also you don't have to have the second halogen coming in, or you could also have a mixed halogen, like a Br and a Cl. The Br will go in first, Cl will kick it out later. So you can have those mixed halogens. Probably not going to get too tricky with that, but I do want you to recognize that it goes through a bromonium bridge if that's the first one on, or a chloronium bridge if that's the second one on. Okay, one more to add to our chart then. So I still have room for, let's see, 12 o'clock and 3 o'clock, so I could do 1:30, 3 and 6, so I could do 4:30, I could do 7:30, and 10:30. So going to do this reaction here. So Br2 in water, we get the OH in back, Br in front, or we get the OH in front, Br in back. It's anti-addition. And then Markovnikov in the sense that Br goes on first, goes to the more crowded, and OH defaults in the less crowded, but not necessarily something going to make a big ordeal about, because usually we end up adding 2 Brs or 2 chlorines, but it is technically Br first, OH second. Because we don't have an H, we don't necessarily use the word Markovnikov, but it's still the same sort of addition. First one on goes on less hindered, second one on goes on more hindered. Okay, we also have Cl2 or Br2, Br2 and CCl4, Cl2 and chloroform this time, decide to do it in ether. Just pointing out that solvent is not as critical as it may seem, but this one goes on where I get chlorines, just like here, where I get an OH and a Br, I get two chlorines. Notice that these two are anti to one another, so just doing priorities, 1, 2, 3, R, but this is in front, so S. So it goes from an S, S. So let me just double check. So 1, 2, 3, H is in the back, so SS, and RR. So you get a racemic mixture. So we're filling our thing in pretty quick. And big picture, when it comes test time, we are going to ask, and I'm saying we, meaning for my class, I'll be asking it, Professor Santos' class will be asking you to predict products based on what you start with, the alkene, and what reagent you add. You're going to have to be able to predict. And that will definitely include identifying enantiomers or diastereomers, as the case may be, and the regioselectivity, Markov-Nikov or anti-Markov-Nikov, or as is the case here, first thing on going to less crowded, second thing on going to the more crowded. And again, when it's two identical, like Cl and Cl, doesn't matter. Okay, so I want to emphasize what's going on here. So show MEOH plus that. So if I were to use the MEOH, and this is just a little note about that, if you use MEOH instead of water, just like we did with the oxymercuration, same with the BR, you put on an OME instead of just the OH. And then mechanisms could be, I've actually delayed it. So I know it says mechanism on the next page, but I'm going to do a mechanism for this one on the next page. And then also I'm going to worry about what if I use MEOH. So kind of giving away my secrets here. So when we do this, MCPBA, I want to write this compound out because it's kind of a unusual compound. So it stands for metachloroperoxybenzoic acid. You don't know this yet, but on a benzene ring, when you have groups on carbons 1 and 3, we refer to that as meta. It's peroxybenzoic acid because benzoic acid, benzene ring with a carbonyl and OH, this is peroxybenzoic because it has two O's. So this compound, hopefully you look at this and you recognize peroxides are highly oxidative, oxidize things. So it can insert an O, and that's what it ends up doing. It inserts an O into this ring, and then the acid-water combination breaks it open. So just like we had from before, we have anti. This time ended up writing both of the centers that it attacks at. So both enantiomers are drawn here. And I want to emphasize anti, but again, no concern with Markov-Nikov or anti-Markov-Nikov because we're adding the same thing. So regioselectivity, none to worry about. Stereoselectivity, anti-addition. So again, when we see anti, that tells us mechanistically one thing went on first. One of the substituents added on first, created steric hindrance on one side. So the second thing coming in had to go from the opposite side. So when we add one of the O's to form that three-membered ring, that O might, let's say it's up, second one has to come in on bottom. If the O is on bottom, second one has to come in from on top. So you create steric hindrance in your transition state, in your intermediate. Regioselectivity, I'm going to erase my peroxybenzoic acid. Yes, under some conditions, meaning here, I don't care. Here, I will care a little bit more because the second one on will be MEOH, and that will select the more crowded side over the less crowded. So the first thing in goes less crowded, second one in gets stuck with the more crowded. And then stereoselectivity, anti. The anti versus syn addition is one of those things that you will see enough times that it becomes a routine, but if it hasn't yet, emphasize anti means one goes on, then the second one comes in from the opposite side. Syn means they both add at the same time. So the epoxidation mechanism. Here's your peroxy acid. I'm just putting an R instead of the chlorobenzoic because other peroxy acids will work. I'm emphasizing this red O because that's my reactive one. The O bond, the peroxide bond is highly unstable. That O can kick in. It's going to be a bizarre connection of atoms. So the first thing that's going to happen is this carbonyl can come out and pick up the H, which makes for this OH bond, but it also creates an unstable carbocation here. These electrons that used to be bonded to the H can now go to this carbon right here. So I now make a bond between the peroxy O and the carbon, which now creates a fifth bond. So these electrons have to go somewhere. They come back to the O, which now creates 2 lone pairs and 3 bonds O, so it's too crowded. So that has to kick over in that direction. So it is this electron flow happening all at once because you would create unstable intermediates with too many bonds to atoms otherwise. But it is just a kind of bizarre movement of electrons. You will eventually learn, if you go all the way to 311, something called electrocyclic reactions, where electrons move in sort of a cascade effect, where when 2 flow, it causes 2 more and 2 more and 2 more in this giant cycle. So if you notice, this carbon is losing electrons to begin with, but they cycle around. It goes here to here to here, back to here, so it ends up getting those electrons. So they are cycling around. So whereas this isn't truly electrocyclic, because we're not overlapping perfectly, it has that same sort of flow. So just follow where the electrons go, and you should be able to figure out what the intermediate is. So in this case, we get this acid, which is this R. This is now the OH, and this is now my carbonyl. And the red O has been inserted into the double bond. Okay, again, because you have tertiary and secondary, it's not a perfectly symmetric triangle, if you will. When we add acid, we protonate the O, and now you're definitely going to see the favoritism, where it's going to break there to form a tertiary carbocation, or then it breaks there to form a secondary. So this becomes the weaker of those 2 bonds. So water, when it comes in and attacks, will attack the one with the bigger delta plus because of that bond being weak. This will come in, that'll break. This is where you have to decide if this is SN1-like or SN2-like, because I'm under acidic conditions here. Under these acidic conditions, acids protonate things and make tendency to make carbocations along the way, which means this is going to be more like an SN1, which is why we're going to favor the tertiary. As this bond breaks, creates a tertiary carbocation, or as this weakens and creates a tertiary partial cation, that O water will come in and attack. So now we have this OH that is now off by itself from the O from before, along with the H that was picked up from protonation. Then we have water here. Simply deprotonates, and you end up with that compound. And again, it can attack from either side. So I could have my peroxide on the upside, and I could have had this OH down and that OH up. I only showed one enantiomer, but you have to keep in mind this will generate an enantiomer. So the mechanism isn't too unreasonable, but as hinted at before, if I decided to use methanol instead of water, I could get an OMe or OCH3 instead of an OH. So you can mess with these mechanisms. And that's one of the things that's going to be really hard to get used to. Know your basics, know your fundamental reactions, and then add in the extra little nuances as tricks you can do to them, not a whole new reaction to know. So our spider chart again. We now have MCPBA, or just in general, a peroxy acid of some sort. Then when I treat it with acidic water, I'll get a diol, but specifically, I will get a trans or anti-addition diol. So the 2 H's are trans to one another. You get anti, just like we have over here. So just please make note of that. You can change the conditions you break it open under. I'm going to stick with mostly what the book does, but again, for every one of these reactions, you can do some small little twist along the way to change what you get. So understand the reaction mechanism and the ideology behind it, the general key points, but be flexible in what can change. So you will not always see H2 and PD, for instance. Like I mentioned, might be instead of platinum, might be palladium, might be rhodium, might be some other metal. Cl2 might be ClBr, for instance. It might not be ether. H2SO4 and water might be a different acid, but again, you want one that isn't a very good nucleophile so that it ends up adding the water instead of the conjugate base. But just be open-minded to the fact that these are good generic reactions, but you can have slight changes in the reagents, but you still will get an anti for here. You'll still get a Markovnikov. You'll still get anti-Markovnikov and syn for this one. The details of the reaction won't change. So know those. Make sure you hang on to those key words that describe the reaction you get. Notice each one has something that it tells you what it is. Absolutely imperative you hang on to that. Okay, so again, we're getting through these well, actually, these videos are now 2 reactions at a time, the mechanisms. I have yet to do any specific examples, practice with these. I'm still just going through one reaction after another. So keep in mind, we are still in the learning phase. Once we have these down pat, then we'll start in the application phase with particular products. But we're going to introduce the concept of synthesis. So you officially arrived as a true OChem person because for every single reaction, you're now responsible for predicting the product, knowing what you get and the key nuances, knowing the mechanism, how it happens step by step, and how can you use this reaction coupled with other reactions to make target molecules. So molecules in design. So I think it's pretty exciting times. And hopefully when you get this arsenal of reactions, after you go through your information overload stress, you start seeing the fun of it, that the mechanisms are all kind of like puzzles. And they're similar, but with slight nuances, slight differences. And that synthesis is just this fun way to look at one compound and figure out there's 7 or 8 different ways to get to this other compound, but what is the most practical? What is the fewest steps? What requires the least workup in terms of stereochemistry? And so the questions that we'll start introducing are more puzzles. Anyway, thank you for sitting through all this, and I will see you at the next podcast. So I'm stopping now. Thanks a lot.